Hi everyone, today we will wrap up this chapter, limits and continuity, with the last part, which is the precise definition of limits, namely epsilon-delta definition of limits. Alright, so yeah, as you know, this is a nightmare of most Calc 1 students. That's why I reserve it as the last part of this chapter. Right? So actually it's very simple. You just have to follow the template that I'm going to give to you. Right? So before we begin with the epsilon-delta proof, let me revise something from the previous lessons. Right? So I think in lesson number 2, when we talk about one-sided limits, I actually gone through the precise definition for it, isn't it? So if we have a function fx and we are approaching some x value, namely c, from the right, okay? So for example, if your c is here and we are approaching from the right, means our x is somewhere here, and we need to define what is the meaning of approach, right? So we say that your x value is within this region. Okay, I'm referring to right hand limits, yeah? I'm referring to this region. And from c to this c plus delta, okay, maybe I should label it below, okay? This is your delta, where delta is a very small positive number. Then what happened when your x falls within that interval? We said that for a right hand limit to exist, your fx must fall within this region. Okay, your fx should be somewhere here. And what is this? This is L plus epsilon, L minus epsilon. Right? So if it is approaching from the left, then now this time your c is here, your x approach from the left, then your delta is still here, hence this will be c minus delta. When your x is within this range, your y value, which is your fx value, should also be in between this range, which is from L minus epsilon to L plus epsilon, where both epsilon and delta are very small positive numbers. Okay, so this is a precise definition for one-sided limits. Then what about from two sides? It's even easier because you just go ahead and combine two of them. So what happens when we combine two of them? Okay, so as you can see here, we are now taking x minus c, the absolute value of x minus c to be in between 0 and delta, which means this times your c is here. I approach from the left, okay, like this, then I approach from the right, and it should be within, from here to here it should be a delta, from here to here it is also a delta. So your x this time now is within this interval from c minus delta, this is a series of, I think I missed out c here, and this is a c plus delta. Okay, then what about your fx? Your fx should also fall between L minus epsilon, L plus epsilon. Okay, so your fx should be somewhere here. Alright, so this is the concept or the precise definition of limits. Okay, so now one more thing to revise, which is the precise definition for infinite limits. Okay, so we say that fx approach infinity, and write this one for fx equals to b is even easier to understand because now you only have to deal with delta, you don't have to care about epsilon. Why? Because your fx is going to infinity. Okay, so if it is from two sides, c is here, your c plus delta, c minus delta, from here to here is delta, from here to here is also delta. Within this range, when your x is within this range, then what happened to your y? You see, there exists a positive real number b, which your fx is greater than b. So if your b is here, means all your fx should be up here. All the fx should be up here. okay, which means the graph should maybe look something like this. Okay, so all the x will fly up to a very big number, which is positive infinity. So this is when we say that, yeah, the limit is positive infinity. Then what happens when we want to say that it is negative infinity? It's the exact opposite. Okay, now your b is negative. So negative b is here. Your c is still here. C minus delta, C plus delta. From here to here is delta, from here to here is delta. So within, when your x is within this range, this interval, then you say that your fx is smaller, right? You see, your fx is smaller than negative b. Means your fx is very small number. Hence, it is actually negative infinity. Alright, so these are the important concepts before you make sense of what you write in your epsilon-delta proof. Alright, so now, if you are okay with this, then we will proceed with the exercises, which you have to prove the following limit statement, which is we need to use the epsilon-delta definition. And I'm going to give you a very simple template to follow. Let's look at question number 1. We need to prove that the limit of 9 minus x as x approach 4 is equals to 5. So this is two-sided limits, right? Which we have to refer to this definition. Okay, so the first thing you have to do is to determine your c, your l, and your fx. Then you just go and fill in the blanks. Okay, so in this case, your c is 4, your l is 5, and your fx is 9 minus x. Am I right? So how to write the proof? Okay, let me just write proof. Okay, the template is very simple, which I'll write in black. Given, choose, then suppose, then we need to check. Maybe I need more space for suppose later, but never mind. So these are the 4 parts of the proof. Okay, so I will go through them one by one. Given what? You look at this. Because we are dealing with what? We are dealing with fx, right? So given your, okay, let me erase everything first. Okay, given your epsilon greater than 0. You see, from the definition itself. Given epsilon greater than 0, which means we need a very small positive number greater than 0, then we need to choose some delta value. And don't worry, we will come back to this later, alright? And this delta must based on your value of epsilon. So we just proceed with the next one. Suppose what? Okay, so as you can see from here, we actually have 2 parts, right? Such that we have 2 things. Suppose that your x is within c plus delta and c minus delta, which means suppose this part. Okay, suppose your absolute value of x minus c is in between 0 and delta. So you just write here the absolute value of x minus c. Who is your c? 4 is in between 0 and delta. And actually, okay, so for now I will omit the 0 because we know that we need to, our delta is actually greater than 0. Alright, the reason I omit 0 because I want to further manipulate this inequality. Okay, so now I have negative. Okay, let me use blue color maybe. Negative. Okay, this is the let me see. Okay, this is actually the template. Smaller than delta. Then this x minus 4. Yeah, absolute x minus 4. Okay, I use this one. Okay, x minus 4. Never mind, I just use red color for. Okay, absolute value of x minus 4 smaller than just now is what? Delta, right? Then negative delta x minus 4 delta. I would recommend you to write it like this first. 4 plus delta, then 4 minus delta. So that later is easier for us to compare. Okay, I'll box this out. You see, I'm running out of space here. Okay, we need to check. What do we need to check? You see, now we already fixed this. And we need to check for this. We need to check whether this is true. And remember, because we haven't fixed the value for delta, so actually we are doing like a reverse thingy, which we set up everything, then we come back to the setup. Alright? We do everything first, then we come back to the setup of delta. Okay? Now we want f of x minus L smaller than epsilon. F of x is 9 minus x minus L is smaller than epsilon. So maybe it's a little bit hard to remember, but how you relate is, you see here, this is actually your x, right? So C is always your x. Then what about this? L. Remember from the graph that we draw earlier, L always referring to the fx. Alright, so just use your fx minus L, then x minus C. Okay? And now what? Just go ahead and simplify this. This will be 4 minus x, then like this, 4 minus x. Okay, I'm running out of space, so I will continue here. And what's next? Okay, because I want to compare my x, right? So I just go ahead and bring the 4 over, maybe negative epsilon minus 4. Then I need to flip the sign, right? Then epsilon minus 4. Now I flip the sign. Okay, this is 4 minus epsilon, right? Because I multiply everything by negative 1. Epsilon plus 4. And now, to make it easier for us to compare, I just like flip it again. Oh, maybe I should write it like this, so that it's clearer for you to see. Okay, and we are done. Now you try to compare the two inequality that I boxed together, these two together. What value should we give to delta such that your both of them are the same? I repeat, what value or what should I assign to delta such that both of these are correct, are true? It's very simple, isn't it? If you compare your delta, if you replace it with epsilon, and you are done, right? You don't have to do anything. And that's the end of the proof. Right? But actually not every time is so nice, because this is the first question, which is the easiest one. You just need to like direct compare. Okay? So sometimes you need to like manipulate a little bit. Then you need to find the smallest one. And I think we will encounter it in the next example, right? So let's go ahead to the second question. Oh, we have a cert. So again, the first thing is to determine your C, your L, and your fx. Then later on, just fill in the blanks. Proof. Given. Choose. Suppose. Then check. Maybe we need more space later. Suppose. Okay, given epsilon greater than 0. Okay, this epsilon greater than 0, this one depending on what kind of limits that you are taking. But in this case, we are actually taking a two-sided limit. So just write epsilon greater than 0. Okay, we will see how it works for infinite limits later. Then choose, I told you, leave it blank first. Delta equals to some value based on epsilon. Then suppose what? Come back to the definition. Suppose this thing, isn't it? Suppose your x first. Suppose the absolute value of x minus c smaller than delta, negative delta x minus 9 delta, bring the 9 over delta plus 9, 9 minus delta. So that is easier for us to compare later. Okay, maybe I think we need a lot of space for this check, so I'm just going to write in the next page. Okay, then check. Check what? Remember? Check this one. F of x minus L is smaller than that. Okay, then who is your f of x? Square root of x plus 5 minus L. Remember, fx over s associated with L is smaller than epsilon. Manipulate x plus 5. I'm a little bit worried about this because we have a square root later on. I don't know how it works. So let's see how it works. Then bring the 2 over. 2 minus epsilon x plus 5 epsilon plus 2. Then you square both sides. Okay, you square everything. Square this and that will cancel. If you expand this one, you'll get 4 minus 4 epsilon plus epsilon square x plus 5 epsilon square plus 4 epsilon plus 4. Am I right? Then bring the 5 over. Okay, let me write it like this. So that is, I think it will be easier for letter. Did I make any mistake? Did I copy the question wrongly? Yeah, I copied the question wrongly. That's why it's so weird. It should be minus. This is what happens when it is not on the same page. You know? Minus. Okay, the reason why I say this is because later on you will see why. Okay, epsilon square plus 4 epsilon plus 9. Oh, actually it doesn't matter because both sides are the same value regardless. Alright, so anyway, now what? Now we have a very complicated, we can't do any further, can't simplify any further. So yeah, let it be just like this. And now we go ahead and compare two of the inequality that we wrote just now. Smaller than. Okay, 9 minus delta compare with this one. And you'll notice that at the end of the day, we'll have two inequality, you know. So I will just go and write 9 minus delta equals to epsilon square minus 4 epsilon plus 9. What do we want? We want delta. So we write delta in terms of epsilon. So delta will just be this 9 and 9 can cancel, and you will get 4 epsilon minus epsilon squared. Okay, this is the first one that we got. What about the second one? So you might be thinking that, will it be the same? Let's try it out. Let's find out, yeah? So delta plus 9 is equals to epsilon squared plus 4 epsilon plus 9. Remember, we want delta, and this 9 and 9 can cancel. Epsilon squared plus 4 delta. They are not the same. So which one should we choose, or should we write something else? The truth is because we are talking about limits, remember? So do you agree that the smaller the delta, the better, right? Smaller delta is better. Because smaller delta means, let me take this one. Smaller delta means your x is closer to c. This is logic, the smaller the delta, the better. Alright? Because smaller delta means x closer to c. So, which one is smaller? Which one is smaller? But in this case, it's actually very obvious. But it's also not obvious. Because you know why? You know why? Because you are, for this one, obviously you will tell me that the first one, this one should be smaller. Am I right? But we are not sure whether the value of 4 epsilon minus epsilon square this 4 epsilon, will it be smaller than epsilon squared? You got what I mean? So if we minus it out, we might end up with a negative value. So in this case, if you are not sure, but actually you should choose the first one. You should choose the first one. Just that if you are not sure, then you just leave your answer like this. Actually, okay, you know what? I will just write 4 epsilon minus epsilon square here. Okay. So in the case that you are not sure, you just write the minimum of 2 of them. Alright? I think we have one question on that later. Okay? So for this question, I will just write like this. Choose delta equals to 4 epsilon minus epsilon squared, so that both of our inequality will meet. Okay? Number 3. Oh, okay, very interesting. First of all, who is your C? 1. Who is your L? 1. Okay? Then now, you have 2 fx. Which one should we choose? We'll deal with that later. We just go ahead write down our template first. Okay? Given, choose, suppose, and I think our check will need to fly to next page. Okay. Given epsilon greater than 0, choose delta equals to some values. Suppose remember, always suppose your x. Okay, absolute value of x minus c is smaller than delta. Manipulate x minus 1 delta, bring the 1 over, 1 minus delta, 1 plus delta. Okay, check. Oh, this is when we need to determine our fx. Let me ask you one question. We are approaching 1. So are we taking x equals to 1? Again, we are taking limits of x approaching 1. Should we take the definition of fx when x equals to 1 or x not equals to 1? Okay, so you know the answer. We should take the x not equals to 1 because we are not on x equals to 1. Hence, we will just write for x not equals to 1, the absolute, okay, sorry, I should use red color. For x not equals to 1, the absolute value of fx, right, minus L is smaller than epsilon. Negative epsilon, x squared minus 1, epsilon, x squared, 1 minus epsilon, 1 plus epsilon. And let me write one more step, or maybe we should go to the next page. Okay, so I just go ahead and square root all of them because on top I have an x, right? So it's better for us to try like this, but be very careful with this. But actually square root is still okay. Reciprocal and multiply by negative numbers, that is what you have to be very careful because you need to change the sign. So now square root and square will just cancel. Then we have 1 minus epsilon x, then 1 plus epsilon. Am I right? And this is the one that we want to compare with. Let me just write it here. Oh, okay, actually don't need. Actually need because we don't have square root for the first one. Then this one we have a square root. You see, I keep on making careless mistakes. Anyway, so in order to make them the same, again we have 2 things that we need to equate, which is 1 minus delta. 1 minus delta must be equals to square root of 1 minus epsilon. And the second one is 1 plus delta must be equals to the square root of 1 plus epsilon. What do we want? We want delta, which is 1 minus square root of 1 minus epsilon. And your delta here would be 1 plus epsilon plus minus 1, sorry, minus 1. Again, we have 2 epsilon. And this time is even harder to determine. This involves square root, right? Very hard to say, but I would say that this one is greater. No, this one is greater. This one is we need something smaller. This one is smaller, right? Because you square root of that number. So but again, you don't know what happened to this one, right? So to be safe, I will just write delta is the minimum. Okay, this is when I show you the trick. You just write minimum of these two. 1 minus square root of 1 plus epsilon. 1 square root of 1 plus epsilon plus 1. Finish. That's it. The minimum of these two will work. Alright? And then make any mistake or not? No, right? This is minus, right? That's why I feel like very weird. Alright? So that's it for two-sided limits, I think. And we'll proceed with the infinite limits. Oh, we have an absolute value inside, which may make our life easier, because remember in our definition we keep on having all the absolute value. I don't know, maybe it will be easier for us to compare later. So let's go back to the precise definition for infinite limits. Okay, so we need to find delta such that f of x is greater than b, and b is positive real number. The template is still the same. Given, choose, suppose, and check. But this time, given, if you refer to the definition, this time we don't have epsilon, isn't it? Where is our epsilon? We can't write epsilon greater than 0. But this time, we have another friend, which is our b. And in fact, you can replace it with any alphabet you like. So given, this time is our b greater than 0, because b is a positive real number, isn't it? Positive real number b. And you have to be very careful. I choose positive real number b because my L is positive infinity. Oh, I forgot. Sorry. And my f of x is 1 over absolute value of x. I got too excited seeing the absolute value. Anyway, this one, right? Because it is positive infinity, so I choose positive real number b. If it is negative infinity, then I would have choose negative real number negative b. Okay? Choose. Still, you are still choosing your delta. You need to mix and match your delta and b, or just now was epsilon. Okay? Then suppose what? Suppose anything related to your c, right? Which is this one. Anything related to your x, sorry. Okay, x minus c in between 0 and delta. 0 x minus c, like this, right? Which is very nice. I forgot. I should have ignored this, alright, I told you. Okay, then this is what? This is actually negative delta x delta, and that's it. And we just have a very simple thing to compare later. Okay, check what? Check the first part, whether your fx is greater than b. fx greater than b. But we have a problem, isn't it? We have a problem because we don't know whether your x is 0 or not. If your x is 0, you know that you can't multiply both sides by 0. Right? So what I will do to be safe, just flip it, change the sign, and now you can do your inequality, isn't it? And this will even make your life simpler, because just now it was absolute value and it's a greater, which is very hard to evaluate, and now it is an absolute value and it is smaller, which is easier for you to evaluate. You can just write it like this, which is very nice because you can directly compare with the first inequality that you have written. So obviously, to make two of them to be true, you just let your delta be 1 over b, and that's it. Very nice, right? And what does it mean? Okay, because like previous question, we didn't actually go and interpret what we have written. So let me just write like this. If this everything is proven to be true, then we can say that just now the definition, okay, actually you should, after all this, you should remember your x minus 0, which is x minus c, smaller than delta, greater than 0, means what? Means your absolute value of x is smaller than 1 over b, which means, actually I'm doing the reverse part. So two of the conditions are met. Fx greater than b. Two of the conditions are met. Now, so by the definition, by the precise definition of one-sided limits, it is infinity. Okay? Number 5. The reason why this is so confusing, because the way we do the work are like in opposite direction. Okay? So the proper way is actually the proper logic actually flows like this. But we are doing it backwards because we want to like cheat a little bit to find our delta. Okay? Then last one. Limit as x approach 3 of that one should be negative infinity. You see? This is why I told you that you have to be very careful with your L. And C, then fx is negative 2 over x minus 3 squared. This is why I told you have to be very careful with the L, especially when it involves infinity, because now if it is negative infinity, you have to choose negative b. Okay, negative b is a negative real number, means, let me write out template, choose, then suppose, check. Okay, given, you see, b is a, negative b is a negative real number. So we should write given negative b, this is a concept, yeah, smaller than 0. Okay, choose delta equals to some value in terms of b, and I think in this case it will be quite complicated. Suppose, remember, suppose is anything related to your x. So you suppose this part. Okay, suppose your x minus c smaller than delta, manipulate, negative delta x minus 3 delta, you should not have your that one modular size anymore. Then you have your 3 minus delta, 3 plus delta. Very nice. Check whatever associated with your f of x. Okay, so in this case your f of x is negative 2x minus 3 square, should be smaller than, be very careful, it is smaller than negative b. Okay, your fx should be smaller than negative b. Smaller than negative b. okay, so like I said, because we are not sure whether this fella here, x minus 3 square, will it be 0 or will it be like negative, I don't know. So to play safe, I would flip it again and I change the sign. Okay, I will make my x on top, negative 2 at the bottom, negative 1 over b. Okay, then I will just continue here. I hope I have enough space. And now what? I multiply both sides by negative 2 and I need to switch the sign again. Okay, so x minus 3 square, switch the sign, yeah, 2 over b. And now, take square root on both sides. And this is where you have to be very careful. Because why? The square root of a square is always positive. Right? If you square root a square, a perfect square, it will be the absolute value of x. It will not give you anything negative. Hence, you should write this as, okay, you still have your x minus 3 smaller than 2 over b. The minimum, not say the minimum, it cannot be negative anyway, so you should write a 0 instead of a negative square root 2 over b. Okay, so this is a thing that you have to compare with your, this one. And now we have, actually, you know what? You should just compare with this one. Delta. You should just compare with this one. Actually, no need to write this step. Compare these two, it will be easier. Right. So, your delta will just be square root of 2 over b. Finish. Then what does it mean? Okay, then your x minus 3 smaller than delta greater than 0 means your negative 2 over x minus 3 square smaller than negative b means your f of x smaller than negative b. And your negative b is smaller than 0, obviously. So by the precise definition of infinite limits, this is actually negative infinity. Alright, so the thing about epsilon delta definition, why is it so like a nightmare, is because the flow of logic is a little bit opposite to what we usually do. Right? Because our final goal, instead of final goal, is like the last step, the last line in our working, is actually on the first line of our working. This is why it's like you are doing the opposite way. Okay? I don't know whether you got what I mean, but if you really struggle with this, then I would recommend you to just follow this template. Alright? Yeah, so that's all for precise definition for limits, and with that we are done with this chapter. Alright? So before we end, I would just like to recap what we have learned in this chapter, limits and continuity. Alright? So the first part, actually we are like jumping here and there, but anyway, what we have learned in this chapter, the first part is actually to evaluate limits graphically, analytically, and algebraically. And I told you algebraically we actually have 5 methods, right, in our first lesson. Right? So we actually, if you would like to rewatch the video of the recorded lecture e-calc class, then you want to revise from here to here, I guess, then you watch video lesson number 1. Okay, then after that we have touched the one-sided limits. Okay, so one-sided limits is actually our video lesson number 5. Special trigonometric limits was number 6. Then limits involving infinity was number 7. L'Hopital's rule and commonly occurring limits are actually lesson 8 and lesson 9. Okay, so if you would like to do revision, then just follow this one. Then after evaluating limits, we actually have talked about continuity and discontinuity, right? And you can find this in lesson number 3. Then the hardest part of this chapter, which is precise definition of limits, we have discussed the precise definition for one-sided limits in lesson number 2. Limits involving infinity and also the asymptotes, we discussed it in lesson 4. And everything, all the precise definition exercises are actually done in this lesson, which is lesson 10. Okay, so with that, we are done with the chapter limits and continuity. The next one would be derivatives. Alright, so that's all for today. See you guys in the next e-calc class.